Depending upon how much you actually played with the Scala REPL and tried different numbers and different operations, you might have noticed a number of interesting and odd things. And some of those things actually relate to the way in which computers store numbers. And for that reason, it's important for you to know something about how the computer stores numbers, because otherwise you could run into problems and you will have no idea what is going on. So to illustrate this, we're going to take and do a little bit of math, but it's math with some larger numbers. This is 2 billion plus 2 billion, which of course, as everyone knows, should be 4 billion, but it's not. At least Scala doesn't think so. Now, why is this? What's going on here? What about 2 billion plus 1 billion? Well, that also seems to have problems. 1 billion plus 1 billion, though, that's perfectly fine. Clearly, something changed between 2 billion and 3 billion. And it turns out that what happened was we hit the limit of how big numbers we can store. So, how are these numbers stored in the computer? Well, it turns out the int type uses what's called a 32-bit binary 2's complement number. And we'll deal with those parts each individually. First is the fact that it's binary. Down in the hardware of the computer, everything is worked on in a binary format. And the reason for that is basic engineering. It's a lot easier to store an on value and an off value than it is to store a 0, a tenth, 2 tenths, 3 tenths, etc. The normal number system that you're used to is decimal. In the decimal system, there are 10 different digits that we can use, 0 through 9. And every number is composed of those 10 digits, and each position in a number is another power of 10. In binary, in some sense we simplify things, we only have 2 digits, 0 and 1. And every digit in a number is a power of 2. So if I give you the number, that works. It's a happy binary number. This is the ones digit. Okay? And there's a 1 in the ones digit, so it has a value of 1. This is the twos digit. If this were a decimal number, this would be the tens digit. But it's not. We're dealing with powers of 2 instead of powers of 10, so this is the twos digit. This is the fours digit, because we multiply each time by a factor of 2. So just like in decimal, it's ones, tens, hundreds, thousands. Here it's ones, twos, fours, eights, 16s, and 32s. Which means that this value is 32 plus 16 plus 4 plus 1. 32 plus 16 plus 4 plus 1. Okay. And indeed, that is how you will probably wind up converting from binary numbers to decimal. If you're given a binary number, you figure out how much every on bit is worth, what its value is, and add them all up. What if I want to go back the other way? Well, there are a few ways to do this. So I have this value 53 here. One way to do it is to note that 53 is smaller than 64, so there's no 64-bit, but there is a 32-bit in it. And then I have to subtract that 32 away from the 53. So 53 minus 32 gives me 21. So I have a 1 in the 32-bit, and then I have 21 left over. Now 21 happens to be bigger than 16, so the 16-bit is on. We can do the math from here completely inside of our head. 21 minus the 16 is 5. 5 is smaller than the 8-bit, so the 8-bit is not turned on. But 5 is larger than the 4-bit, so we get a 4. When we subtract 4 from the 5, we're left with 1, so there is no 2, and there is a 1, and that was indeed the binary number that we started off with. That's one way of converting from decimal to binary. Actually, I prefer a different way myself, and while that approach builds numbers up from the high digits to the low digits, The approach that I'm going to show you goes in the opposite direction. So I'm going to start off and take my 53 and I'm going to do a modulo 2. Remember, modulo is the remainder after division. And when you do a modulo 2, it's basically telling you whether the thing is even or odd. This number is odd, so we get a 1. And then I'm going to take that 53 and I'm going to divide it by 2. And I'm left with 26. And so I take that 26 and I modulo 2 and I get a 0 because it was even. And I take that 26 and I divide it by 2 and I get 13, which is of course odd. So when I do the modulo, I get a 1. 13 divided by 2 gives us 6. 6 modulo 2 is 0. 6 divided by 2 gives us 3. 3 modulo 2 is 1. And 3 divided by 2 is 1. And we can stop there, because then we have the 1 modulo 2, which is 1. So if we take all of the columns where we did a modulo and we go up them backwards, 1, 1, 0, 1, 0, 1, which happens to be the binary representation of 53. If we weren't 100% certain, turns out that in Scala there is a method called toBinary and sure enough, 53 converted to a binary string is 110101. Okay. So now we've seen what binary numbers are. We know kind of why we care, because they can impact some of the results of our mathematical operations, and we've seen how to convert to and from binary in some different ways.